All right, everyone. Getting into section 4.5 today, we're going to talk about limits as x approaches infinity or negative infinity. So in the last video for section 2.5, we talked about how when a function has a vertical asymptote, we can kind of see that with the limit as x approaches the asymptote. Well, one of the important things about function behavior in general is knowing the end behavior, meaning as a function gets closer to the end of its domain on either side, what is the y value doing? So to kind of get an idea, let's go back and review something from algebra. So if I have rational functions, let's say I have these three rational functions, I want to describe all of the asymptotes on them. Generally, when I see a rational function like this, the first thing I want to do is try and factor, if I can, to note any removable discontinuities that are on the graph. So if I look at the denominator for this first one, I notice that that's going to factor. So numerator, we've got x plus 1. Denominator, we have that's going to factor to x minus 5 times x plus 1. And I notice that I have a factor of x plus 1 in the top, a factor of x plus 1 in the denominator. So those divide, we leave behind a 1. And from the last video, we know that this means the graph of that function is going to look the same as the graph for 1 over x minus 5, with kind of an extra detail here that x cannot be negative 1, because there's a removable discontinuity or a hole at that value of x. So if I had to describe all of my asymptotes, from the last video we know that the vertical asymptote is going to be whatever makes the denominator 0. So we have a vertical asymptote when x is equal to 5. Not negative 1 though, because remember that's a hole, that's a removable discontinuity, it's not the same thing. Horizontal asymptotes though, we had rules, for those with rational functions, and it kind of depended on the degree of the top versus the degree of the bottom. So if I look at the degrees, numerator I only have a constant, so that's a degree 0. Denominator I have a linear, that's degree 1, right? And another way to think about it is, what is the highest exponent for x? Here the highest exponent in the denominator would be 1, and since there is no x in the numerator, highest exponent is 0. So the degree is bigger on bottom. When that happens, we have a horizontal asymptote at y equals 0. Yep, bigger on bottom, 0. Bobo, if you wish. And going on to the next one, right? In my numerator, I noticed that we have a cubic function. We don't have any GCFs we can factor out. We don't have any common factor for the first two terms and last two terms. So we can't factor by grouping. There's not really any easy way to do that. But that's fine, because we can go ahead and just look at what our asymptotes are going to be. So again, the vertical asymptote, I'm going to get anything that makes my denominator equal to 0. So that's going to be 2 minus 4x cubed equals 0. And then if I move the 4x cubed over, we get this equation. Divide both sides by 4, we get x cubed is equal to 2 over 4, which is the same thing as 1/2. And finally, if I take the cube root of both sides, I end up getting that x is equal to the cubed root of 1/2. Note, I don't need a plus or minus here because I took an odd root on both sides. I only need to do the plus or minus if I take the even root of both sides. So square root, fourth root, sixth root, etc. So we have a vertical asymptote there, one single one. Horizontal asymptotes, again, we have those rules that you learn in algebra class about rational functions. So looking at the numerator, the highest exponent for x is 3, and the denominator, the highest exponent for x is also 3. So they have the same degree. Whenever the numerator and denominator have the same degree, we divide the leading coefficients. So you take the coefficient for the x cubed term on both sides. Top, it's 8. Bottom, it is -4. And we divide them. 8 over -4. So we get a horizontal asymptote at y equals -2. All right, so those are the asymptotes for the second function. Now, little mnemonic to remember that one, EATS DC, exponents are the same, divide coefficients. Fun. And then the last one, we've got a degree 2 polynomial in the top, a degree 1 polynomial in the bottom. All right, so the degree is actually bigger on top. Whenever that happens, bigger on top, we get an oblique asymptote or a slant asymptote if the degrees are only 1 apart. So in that case, we actually have to do long division to figure out the equation of the asymptote. Of course, we can still figure out the vertical asymptote without doing much of anything, because remember, that's just what is going to make the denominator 0. So if I substitute -1 for x, that would make my denominator 0, so that's where I have my vertical asymptote. For the horizontal asymptote, though, that's where I need to do my long division. So doing some long division. So we're dividing 2x squared plus x minus 5 by x plus 1. So remember the way this works, look at just the first terms. What do I multiply x by to get 2x squared? I multiply it by 2x. Then I distribute, so we get 2x squared plus 2x, and we're going to subtract that. Notice the parentheses. So 2x squared minus 2x squared is 0. I don't get anything there. X minus 2x, I get -x. And then you bring down the rest. So -5. So then, first term to first term again. What do I multiply x by to get -x? Well, I would multiply by -1. So when I distribute that, I get -x minus 1. We're going to subtract that, and that's going to leave us with -4. So I have a remainder then of -4. And I know to stop because what I have left over is lower, has a degree that's lower than my divisor x plus 1. So when I do my long division, that's what I get. When we are only looking for the equation of the oblique asymptote, we don't actually do anything with the remainder. If you wanted to, you could actually just rewrite that function, and that's something that you'll have to do later on, either at the end of this course or somewhere in Cal 2, where you rewrite the original function using the remainder, and it would end up having the same asymptotes. So with that said, our horizontal asymptote is going to be a slant asymptote with the equation y equals 2x minus 1. Right, 2x minus 1, which comes from our long division. Again, we kind of just ignore the remainder for the purposes of writing the horizontal asymptote. Okay. So now, now let's actually take what we figured out. Give myself some room here. So now let's take what we figured out about these three functions and use them to evaluate some limits. So first up, let's look at the limit as x approaches infinity of x plus 1 over, x plus 1 over x squared minus 4x minus 5. So that was the first function that we looked at, okay? As x approaches infinity, y is approaching the horizontal asymptote. So if my horizontal asymptote was at y equals 0, then the limit as x approaches infinity is 0. And now if we look at a similar limit, we're looking at the limit as x approaches negative infinity of that same function. So because this ends up working out the same, like if you think about the graph of this function, whether x is approaching positive or negative infinity, the y value is approaching the horizontal asymptote. There's no change there, so the limit is still 0. Now let's look at this limit. Limit as x approaches infinity of x, or 8x cubed plus 4x minus 5 over 2 minus 4x cubed. So that's the second function that we looked at. So as x approaches infinity, the y value is approaching the horizontal asymptote. And we said for this one that the horizontal asymptote was leading coefficient over leading coefficient because the top and bottom have the same degrees, which means that as x approaches positive infinity, y approaches negative 2. And we can say the same as x approaches negative infinity because, again, the y-coordinate is approaching whatever my horizontal asymptote is. So that's also going to be negative 2. Where it gets kind of weird and different is when we look at that third function. So in that third function, the degree in the numerator was bigger, which meant that we had a slant or oblique asymptote. So there's some end behavior associated with that. Now, if you go back to where we actually found our equation for the horizontal asymptote, right, it's helpful for us to note kind of what direction the line goes in. So because 2x minus 1 has a positive slope, I know that the asymptote is going to be like a diagonal line that's increasing like this. So as x approaches positive infinity, the y-coordinate is approaching that line, and, well, the values on that line are getting larger and larger. So that limit would be infinity. Right, and again, as x gets larger and larger, the y-coordinate gets larger and larger, more positive. Now, if we look at the limit as x approaches negative infinity, right, the y-coordinate is approaching this slanted asymptote. So the y-coordinates are getting more and more negative. So as x approaches negative infinity, y approaches negative infinity. Now, the thing that you have to be careful about here is when you have slant or oblique asymptotes with negative coefficients, because then, well, the end behavior might be a little counterintuitive. So for example, if this were negative 2x minus 1, all right, change color for a sec, then my asymptote would have looked more like this. So you see, as x approaches negative infinity, that the y-coordinate on that asymptote would be increasingly positive. So really just look at the slope of your slant asymptote. If it's a positive slope, then it looks like what I drew here. If it's a negative slope, then it just goes the other way. Right? And use the direction of that slant asymptote to guide what you put for that infinite, or that limit at infinity. Okay. Now one that we haven't already pre-screened. So we're looking at the limit as x approaches negative infinity of x minus 3x squared over x plus 4. So just by looking at that rational function just straight away, we notice that the degree is bigger on top. It's a degree 2 in the numerator and a degree 1 in the denominator. So that's going to be another case of an oblique asymptote. Since the degrees are 1 apart, I know it's going to be a line, a linear function. If they were 2 degrees apart, then it would be in the form of a parabola, right, et cetera, et cetera. So with this one, I'm going to look at my highest powers of x in the top and in the bottom. Okay, so I noticed that in the numerator, my highest power of x has a negative coefficient, and in the denominator, my highest power of x has a positive coefficient. That means when I go to do my long division, right, if I do that, I would end up finding that my asymptote has a negative slope, which means that it's going to look like this. So again, I'm going to use the direction of that line to guide what I write for the limit as x approaches negative infinity. So as x approaches negative infinity, we're going this direction, right? And the y values are getting more and more positive, which means that this limit is positive infinity, even though x was approaching negative infinity. So with that one, remember your rules. Bobo, bigger on bottom, 0. Eats DC, exponents are the same, divide coefficients. And let's go with bots. Yeah, bigger on top, slant. Do long division. All right. So one last little topic to look at in this section, relative growth rates. So what we just saw with rational functions is actually a kind of special case of a more broad topic called relative growth rates. So the reason that those work the way they do is because if a polynomial has a higher power, think about it, in the long run, it's going to grow faster than a polynomial that has a low power. So going back to some of the examples we looked at for this first one, my numerator is a linear, my denominator is a quadratic. The quadratic is going to grow a lot faster. So as x gets larger and larger, the denominator is getting much, much larger than the numerator. So if I have a smaller number divided by a really, really huge, gigantic number, then the value of that gets smaller and smaller, which is why we arrive at 0. Or for this one, both the numerator and denominator are cubics, which means they grow at the same rate. The only thing that's going to be different about them is the coefficient. Or if we look at this bottom one, the top is growing a lot faster than the bottom. Right? Since the top is growing a lot faster, that means the overall value of the number is getting larger. So if we expand this to all the different kinds of functions that you might have to deal with here, you can think of having a slower growth rate as being a lower degree, right? So generally speaking, logs have the slowest growth rate out of all of them, because if you remember, the graph of a log is the bendy straw. So as you get further and further out, that just flattens, right? So it's growing at a very slow rate. As x approaches infinity, the log of x does also approach infinity, but it does so very, very painstakingly slowly. Right? For context, log of 10 is 1, but the y value doesn't actually reach 2 until x is 100. It doesn't actually reach 3 until x is 1,000. Right? So order of magnitude there. That's why it grows so slowly. And on the flip side of that, exponentials grow pretty quickly. In fact, they grow faster than power functions or polynomials. And then the last one we have is what's called a factorial. And it's definitely something that you're going to need to know for Cal 2 when you talk about series, right? Or even if you take stats and you learn about combinatorics, right? But a factorial we represent with an exclamation point, and essentially it just means that you multiply x by every positive integer that comes before it. So for example, 5 factorial would be 5 times every positive number that comes before it. Whole number only. Otherwise, you start getting into gamma functions, which are a different beast altogether. So 5 factorial would be 5 times 4 times 3 times 2 times 1, right? Which works out to 120, right? But that's what a factorial is. Really, all you need to know right now is that it grows faster than even exponentials do. So if you see a factorial, that's pretty fast. So let's look at some examples. First one, we want the limit as x approaches infinity of natural log of x over x to the 99. So natural log of x is a logarithm. X to the 99 is a power function. Logarithms grow slower. Polynomials grow faster. Since the fast one is on the bottom, it's kind of like having a bigger degree on bottom, which would mean the limit is x approaches infinity is 0. When we look at the next one, we're looking at x times e to the x. And normally this would be a bit of a concerning thing, because if x were approaching positive infinity, that exponential would be blowing up and this limit would be infinite. But here you kind of have to pay attention to this little detail, negative infinity. That means that we're plugging in negative values for x. And if you remember from algebra, your rules about exponents, if I have some base raised to a negative power, that's the same as 1 over that same base raised to a positive power. So if I look at this limit, I'm plugging negative values in for x. So it would be equivalent to, if I were doing the limit as x approaches positive infinity, of negative x divided by e to the x, right? E to the negative x in the numerator can move down to become e to the x in the denominator. So what I notice now is that I have the faster thing in the denominator, which means this limit is also 0, bigger on bottom. Okay, and then looking at this one, we have the limit as x approaches infinity of x squared over e to the x. All right, we don't have any weird things going on there. We're just plugging in very large positive numbers for x. And we notice that the faster function, the faster growth rate, is on the bottom. So that would be 0. Now, just for good measure, let's say I have, just as a bonus example, something like that. Well, I noticed that, oh, oops, didn't mean to do that. Natural log of x. There we go. All right, so in this case, what's different from the other examples we've done is the fact that our fast thing, our function with the faster growth rate, is in the numerator. That means that the top part of the fraction is getting bigger a lot faster than the bottom. So the overall value of the number is getting more and more positive the larger x gets. So this limit would be infinity. All right, so with these, you kind of have to think, where's the fast thing? Do I have to worry about negatives causing issues, etc.? Oh, I got one more fun one for you. Okay, let's say we want to evaluate that limit. So to kind of drive home this idea of using intuition, if x is approaching infinity, then imagine that I'm plugging in a very big positive number for x. Well, what's that going to affect first? It's going to affect the 1 over x. Because if x is a very large positive number, then that means that 1 over x is approaching 0. And if 1 over x is approaching 0, then sine of 1 over x is approaching sine of 0. And sine of 0 from your unit circle is 0. Now, had this been cosine of 1 over x, your answer would have been 1, because cosine of 0 is 1. All right, so just some other interesting things to think about as you go through these limits at infinity. And that's all, folks. See you next time.